Oh, it's 11:01. We can get started. Good morning, everyone. So my name is Bruno Azeredo. I'm a professor in manufacturing engineering at Arizona State. And on behalf of the organizing committee, welcome to the MateriAlZ seminar series. This is a seminar series that is held in partnership between material scientists, enthusiasts, like me and others, between your University of Arizona and ASU to promote our field in Arizona and beyond. One of the things we want to let you know is that we have not only a website, but also a presence on the various social media platforms. So if you want to continue to receive notifications, we encourage you to look us up on those various platforms. This is our second year that we're doing this. And actually, I want to thank my co-organizers today, Christina, Ankit, and Krishna. They are the ones that actually started this last year. And I just came on board and I'm helping. And I want to thank some of the people on the line today, colleagues, staff, and friends who helped me put this together and share the news of the talk. And also welcome Joseph today. Joe, unfortunately, Zoom, one of the things that Zoom hasn't figured out is how to clap in an enthusiastic fashion. But somehow, yeah, I hope you feel that today. And so it's my distinct pleasure to introduce Joe. He's now the Sanjeev Samgambhir Professor in Radiology and Chemical Engineering at Stanford. After receiving his bachelor's degree from Liberal Arts College, Ursinus College, and a PhD from Virginia Tech, he began his career in 1990 as an assistant professor in chemistry at the University of North Carolina at Chapel Hill. He worked there for nearly 28 years, holding joint appointments with North Carolina State, as well as multiple departments across both institutions. At the beginning of his professorship, he received the NSF Career Award and the PCASE Award for his work in green chemistry, particularly on supercritical fluid pathways to polymer synthesis and thiophene-based monomers. A few years later, he went on to take several leadership roles and receive many awards whose titles reflect his evolving research directions. To name a few, between 1999 and 2009, he served as the director for the NSF SDC on environmentally responsible solvents and processes. And right after that, he became the founding director of the Institute for Nanomedicine at UNC Chapel Hill. And I'm skipping several of the other many things that he has done, highlighting just a few things. But over the last decade, Joe became a preeminent figure in the advanced manufacturing community. In 2015, he published his first work on CLIP, a continuous photopolarization process for additive manufacturing. And in that same year, co-founded Carbon and served as its CEO until 2019 and is now the board chair. Carbon went on to commercialize scalable polymer additive manufacturing, and more recently, his work on 3D printing is going into the micro and nano scales and serving applications in translational medicine. Throughout his career, he has mentored 80 PhD students, and that's a 80, half of whom are women and members of underrepresented STEM groups, underrepresented groups in STEM. Joe is a vocal advocate for the role that diversity plays in innovation. And I picked a quote from Joe from one of his prior talks that goes like this: being intentional about human diversity, we risk detracting from the opportunity that exists to achieve innovation and societal impact. At least but not least, between 2005 and 2014, he was elected to 3 national academies, including science, medicine, and engineering, and awarded the 2015 National Medal of Technology and Innovation by President Obama. With that, please welcome Joe. And Joe, we're asking you to unmute.
Yeah, no, it didn't give me permission until just now, so thank you. Well, it's great to be here. It's great to see the turnout, and I want to thank Bruno, Krishna, and Christina for the invitation. There was almost a little bit of a fight between Arizona State and University of Arizona on our pre-call. And so, but it's good to see the whole state, and it's great to connect with everyone. And now you also have Tim Long on the team there, and Tim was responsible for mentoring me in graduate school. He's a couple years older than me, and I was a junior student in his lab. And it's great to have Tim in Arizona, and good to see everyone. So let me share my slides. And again, it's really terrific to have everybody join here. As was mentioned, I'm now at Stanford. My career has been heavily on the East Coast, UNC and NC State, and a lot of it has been translational. And we like to think about working on projects that can move into the marketplace and really to help people in a lot of different ways. And what was mentioned, it's actually started at Carolina in 1990, so it's was 30 years. But the last 6 of which I was on leave leading a company, Carbon, and we moved from Chapel Hill to Silicon Valley. And I told the investors asked me to lead it. I had already hired a CEO, and I told them all the reasons why it's terrible to have a faculty member lead a company. And despite that, I agreed to do it for a year and ended up doing it for 6 years. And now it's under the leadership of Ellen Coleman, the former CEO of DuPont. So it's really great to see such strong leadership there. And I got my life back, and part of that is rejoining the faculty now, this time on the West Coast, and also on the board of trustees at National Geographic, which I treasure as one of the oldest educational environment or organizations in the world. My team, really privileged to have an amazing team here. A lot of great students. Madison Driscoll is a University of Arizona ChemE, so great to have the Arizona connections there. And but my students come from chemical engineering, material science, bioengineering, chemistry, mechanical engineering. It's just a great group of folks that it's privileged to be part of this group. I'll also talk a lot about the work we did at Carbon and continue to do, and it's an amazing group at Carbon, and it was a privilege to hire everybody and start from zero and get to almost 500 people, and we raised about $680 million and built an amazing organization of people and partners in the field. And I think especially nowadays, especially what we've been through with COVID and George Floyd and the like, I think it's important for everyone to be intentional and clear about their values and what's important to them. And if you go to our website, you'll see this on our website. And really, this is just a welcome mat for people to be clear about, what we do and what we stand for, so that we can be a destination for excellence wherever it is. So this is really important to us. I think a lot about what we do is translational, and a lot of it is focused on making a difference. And I love this quote from Henry Rosofsky: "Research is an expression of faith and a possibility of progress. That leads scholars to study a topic has to include the belief that new things can be discovered, that newer can be better, and that a greater depth of understanding is achievable. Research, especially academic research, is a form of optimism about the human condition." And I think that speaks volumes of how we think about things, whether we're working on infectious diseases, food, lowering healthcare costs. All these things matter a lot. And I think it's this mission really drives us. And in this context, we're thinking a lot about manufacturing nowadays. And like everybody in Arizona, congrats on the amazing initiatives that are underway in Arizona to continue a leadership role. For us, we look at molding. Molding is a tried and true way of making things. Here I'm showing you metal, but you also think about polymer molding, where you heat a material into a liquid state, let it fill a cavity till it wets all the nooks and crannies of that cavity, let it cool, open up the cavity if you have the right symmetry, and withdraw your object. And this is the way a lot of polymer products are made. These injection molding tools, it's not uncommon for these things to cost upwards of $1 million if you're making deep cavity electrical connectors, maybe making 6 connectors at a time. Maybe take you 6 months to get your hands on it. All your intellectual property is wrapped into this device. And once you have it, you don't want to change it because you just, invested a lot of money. It took a long time to get here. And it's in many ways, it inhibits innovation because of the challenges of locking in for a long period of time to get the ROI on that device, and you can only make limited products. Well, what is the magnitude of this technology? Manufacturing is a $12 trillion marketplace. Polymeric products is 1.1 trillion of that, and 30% of that's injection molded. This is a massive industry that's made using an analog molding approach. Clearly things are designed digitally, but this molding technique is the tried and true way of making things. And in this context, a lot of people are looking at 3D printing. Really a fun book here, pointing out the complexity and zero lead time. And everybody in the room on the Zoom call knows what we're talking about with additive. So I don't have to spend much time on that. When we look at, and I'm going to focus on polymer manufacturing. And when you look at polymer-based additive manufacturing, I think they come in some general different categories. The fused deposition modeling, where your molten polymers coming out of a nozzle, really a tried and true way of making things in a layer by layer approach. There's also the stereolithography approaches, pioneered in Japan and further developed in the US and other places. Using light to cure liquid resins, again in a layer by layer approach. And then the powder sintering processes, where a powder goes down layer by layer, it gets sintered, and you develop products. When I think about things from a durability or impact in manufacturing, I think there's probably an argument to be made that SLS is doing the lead right now. Just from a volume of products made in this regard. And when you look at SLS centering, this is an example where you're going to see a blade spreading powder back and forth, and a laser hits it, centers that powder, and this block of powder is getting pushed into the table. And then you'll see the block emerge, and then buried in a block supports the part, and then buried in that block somewhere are the parts. And this is the way a lot of products are made. This is a slow process. There are people trying to speed it up, but unlike metals, where this is really important process, an atomic solid, what we're basically doing here is a molten polymer, and the properties of a polymer are all derived from chain entanglements. And so the faster you go, the less time there is for these particles to fully develop the chain entanglements, and it leads to issues regarding the mechanical properties. And so I think all these processes are clearly layer by layer approaches. And I think 3D printing is often better thought of as 2D printing over and over and over again. And the challenges relate to the fact that it takes a long time. It's still pretty slow. Because of the layer by layer approach, there's anisotropy intrinsic to the properties. And because for polymers especially, the lack of full development of chain entanglements between layers and particles are a challenge, and the material choices are far too limited. Well, and I'll show this video. It seems to be iconic in so many ways, but the idea that couldn't a 3D printer be more focused on products rising out of puddles of liquids? And that was really what we were trying to accomplish, and thinking about something coming out of a puddle where the mass of the part is derived from a puddle of resin underneath the part as it's growing. And in that context, this is a little bit of the way we were thinking about these things, in that we would have a DLP light source. In our case, we're operating at 385 nanometers, but there's a lot of different ways of projecting the light that you can think about. The key for us was, how do we have an asymmetric bonding of a part anyway, so try to cut to the chase. So we're using light through a very special window that is optically transparent and permeable to oxygen. And with that, that allows us to asymmetrically bond the part to the platform and not to the window. And so we're creating a dead zone that is basically a mechanism for resin renewal. So unlike some things in the literature that are misstated, this is not about adhesion. This is about creating a pathway for mass transfer underneath the part. So how do you get a mechanism whereby liquid can flow underneath the part and not be cured? And so that you actually can create a mass transfer opportunity. And I'll show you that through optical coherence tomography. So basically, as part gets pulled up, we're using suction forces to pull liquid underneath the part. And so this allows us to go 100 to 1,000 times faster by using this approach. And the key to this is this window. We've got a lot of experience in fluoropolymers, and this is a Teflon AF material, an amorphous form of Teflon that is among the most oxygen permeable materials known. It's resistant to organic solvents, and it's optically very stable. And so what's happening here is, again, with optical coherence tomography, this pathway, this gap we call the dead zone, is about 20 to 80 microns, depending on the details of how you're running the process. But it allows resin to flow underneath the part and get to the deepest pixel. So it's way more than an adhesion issue. This is a mass transfer opportunity. And when you look at the details of what's happening, we have, this is a z-axis going from the window up into the liquid resin. And then we have a general concentration axis here, where you're looking at the intensity of light as highest at the window as it exits the window. That light is generating radicals through a photoinitiator decomposition. And so the radical concentration is basically tracking with the light intensity as a function of distance from the window up into the liquid. Now that light that generates those radicals have one of two fates. They can kick off a polymerization, or if there's oxygen present, they will get consumed. And the rate of reaction with oxygen is far greater than the rate of initiation of a polymerization. And so what happens is those radicals closest to the window are consumed by the oxygen until the oxygen concentration gets below a certain threshold at which the polymerization will take place. So it's just like free radical polymerization. You want to kick it off, you degas your monomer. And this is what's basically happening as we kick this off. And so we have a very detailed digital twin of the process. It's evolving and really getting extended. That I think of this as a software controlled chemical reaction to grow parts. We take into effect the reaction kinetics, the resin viscosity, the light interaction, heat and mass transfer. All these things come together to give us an increasingly sophisticated view of what's happening in our process. And mechanics plays a really important role because of the Stefan adhesion forces of the liquid gap between here. There's a lot of forces on the part that's working to pull the part off the platform. So you got to balance all these things. And if your part is gelatinous, it can deform as you're pulling it, trying to go faster and faster. So there's a lot to think about. And we've got some ideas in that regard that I'm going to hold off talking to you about now. But what's really interesting about this process is it's different in the sense that it's not traditionally, you don't have to run it always in a layer by layer approach. I love this little study here just to show you exactly what's happening. But if you take this test pattern and you divide it into 100 micron slices and you print it continuously, what that means is that one given image will stay projected for 100 microns in Z. And then once you get to that threshold, you'll change the image again. And it'll go another 100 microns in Z and change it again, okay? Well, we could divide that image 5 times more frequently at higher resolution. And all that means is that the images are changing faster, right? And you're just putting 5 more slices into every 100 micron slice. Well, we can go even faster and at a higher resolution. But these are all done at the same print times. We're just varying the images, right? So if you wanted to do a traditional layer by layer approach and you went from 100 micron slices to 1 micron slice, you would slow it down by a factor of 100. Here, they're all at the same print speed. We're just changing the images. And that's what continuous processing allows you to do. Gets to really smooth surfaces when you do it this way. And it also leads to isotropic parts. Because if you slice open a traditionally polymerized or made part, you'll see the individual layers leading to anisotropy depending on the orientation of how you print them. When you run these free radical 100% UV curable systems this way, you can get to isotropic parts. So that's the nature of the clip process. Now, UV curable resins in and of themselves leave a lot to be desired on mechanical properties. It's hard to get 100% UV curable to have a wide range of properties you'd want for a given application. And so what we decided to do, since we're printing much faster, is could we get into the reactive liquids, which is a tried and true way to make a lot of different polymers, where you can take a epoxy system and tube A and tube B of a reactive system. That's a great way to make great polymer parts, but most of those react too fast to be useful in a 3D printing process, so they hadn't been explored before. But most of these are also not UV curable in combination. So we combine those, we call that dual cure. And just to give you one example, you can take a free radically curable system like these methacrylate based systems, and you can have about 10 to 15 or 20 volume% of this component, and you can have it with the traditional step growth polymerization here, a diapoxide and a diamine. Here we're using aromatic amine. It's a little bit longer pot life. They don't have to worry about Michael addition here with the methacrylates. But you can basically combine all this chemistry. You can print it with light at 385, and that defines the shape of the part. And then you have this latent chemistry there that you can fully drive to completion. And we're basically making co-networks with a wide range of different step growth materials with defining a shape with the UV curable. So this is orthogonal chemistry that's running in parallel to make co-networks, if you will. And depending on the nature of the step growth, you can make a wide range of materials. I love polyurethanes. McGrath, Wilkes, that whole team at Virginia Tech really led a lot of amazing things. And when you take polyurethanes, you vary the hard segment, the soft segment, the chain extenders, you can make amazing products. And depending on the ratio of these components, you can make rigid materials. You can make linear rigid materials. You can make thermoset rigid materials. You can make elastomers. You got lots of choices. And there's a lot of us thinking that, a polyurethane economy is going to be really useful for recycling and a circular economy, because those are reversible chemistries. And we're excited about that direction. I'm not going to speak much about that right now because it's early days for us. But look at what kind of properties you can get. This is a rigid polyurethane with a TG of higher than 120 degrees, high modulus, amazing tensile strength, and ductility. This has got a behavior that looks a lot like a thermoplastic. And so look at these comparisons of notch izod versus heat deflection temperature. The RPU 130 is sitting here, and this is a placard that got impinged by a projectile, and you can see ductile deformation. These are some placards made by SLS in a fracture, a polyamide SLS system. Uh-oh, I'm losing my internet again.
We can still hear you, Joe. So not all is lost. We can still hear you.
All right.
No, we lost you a little bit. And now we lost him completely. Tim, come back up, Tim.
All right. Well, you know, I think Joe's point about an all polyurethane economy is, you know, it's a pretty amazing perspective. You know, it's he's thinking about block copolymers, and you basically can access thermoplastics to elastomers right within the same polymer family. And this really agrees well with some things that are happening at Adidas, right? They're making an all polyurethane tennis shoe, right? So ideally, you'd throw that tennis shoe into a digestion depolymerization process, and out comes the components. So I think what he's talking about is minimizing the types of polymers we have in the world, getting the right polymers, right? Not necessarily having 100 different kinds in our car, but maybe only using 10 different types. So I think that's what he's kind of getting to is kind of minimizing, you know, the number of polymers in our world, and then but finding that family of polymers that can satisfy the range of physical properties that we need. And I think that's a really unique perspective that Joe's, you know, really advocating. So
I know Doug Loy at U of A has been working on the similar and related areas to. Right, Doug, you can unmute yourself a little bit if you like.
You're making this into an interactive seminar.
Well, we had a buffer time after his talk. I'm happy to announce that's that we are scratching that. Your meeting with Joe afterwards is done. We're going to try to use the extra time we have to give him as much time.
I don't have anything embarrassing to say about Joe. He's always been one of the most magnanimous and generous people I've ever run into. For folks that are getting started and folks that are muddling along like I do.
All right, so this is, you can do this with polyurethanes and elastomers and get a wide range of properties associated with that. And this really opens up the opportunity for doing a wide range of different polymeric materials using this approach. And so part of this too was extending it to a technology for the printers, and developed a printer with 75 micron pixels and 160 micron pixels with different build areas. The L1 is 5 times the build area of the M2. And that allows us to begin putting factories together using digital manufacturing. And also, as far as dry back-end processing, thinking about environmental stewardship, instead of using solvents to rinse the parts, we are using centrifugation to spin off excess resin before the second step for polymerization, and collect all the resin and reuse it. So this is very atom efficient using this approach, but it also allows us to digitize every particle or every part. Every part's got its unique data matrix, and that allows us to basically think of every part as being alive, because every part has a unique record in the cloud. And we know its birth certificate, we know which data file, which lot of resin, which printer, which time. We also know which it's the properties, so its grades in school, and even its death certificate for recycling. Can you guys still hear me?
Yes, Joe. The videos are not playing so smoothly, but we can hear.
Okay, I'm going to skip the next video just because of that. But this is really an ultimate opportunity for manufacturing in lots of different industries, including from automotive on consumer products. I rank the opportunities in manufacturing based on regulatory hurdles. Consumer products is a low bar. In other words, if you meet performance and you meet cost, you can scale. Automotive, there's a lot of regulatory hurdles. You know, Ford quality standards takes years to come by. and healthcare and semiconductors are really high. And so dental is an area that we've got, and nothing better to think about the interface of unique digital personalization as you think about in oral health. And so that's a wide range of different materials, different products that really build off one another. And this has been a big one for us as we think about the program with Adidas. Adidas makes 500 million pairs of shoes a year. We'll get to 10% of that is our plan. And we're in single digit millions now, but it's pretty amazing growth, and the prices come down. But what's really important here is I think one of the newest and most exciting areas on the horizon for material science is the interface between architected products and material properties. Bringing those together in unique ways allows one to make products that heretofore haven't been possible, and also allow you to think about scaling up. I mean, getting products that are now scaling to allow pricing. These are still expensive, but the volumes are getting up there now that you can start really driving a cost-effective product. And I'm not going to play the videos, but you can watch this idea about shear forwarding, and it's really a transformation in performance that I think is just a tip of the iceberg that we're beginning to see. Also heavily focused on bio-based materials. This reduced breaking due to the shear forwarding and cushioning. It's a pretty amazing products. And because of higher modulus and great elasticity, you can start really dematerializing the parts for really great lightweight. So we've been excited about this partnership with Adidas. But what's interesting is that these things become, in a bowling alley, this becomes the first bowling pin, and really looking for cascading impact by leveraging materials, leveraging lattice designs and the like, and performance. And again, this idea that architecture allows one to design materials that are stiff or flexible, energy returning, energy dissipating, and it really opens up a whole new horizon. Again, with precision, you can reduce the diameter of struts, really open up material properties in a tunable way. You can start getting into amazing new kinds of lattices, and these surface lattices inspired by block copolymer morphologies, but at the macroscopic scale. They're self-avoiding, so you can really study buckling behaviors in unique ways, and we've built a lot of the tools for doing this now, for designing. And then some of our favorite athletes are wearing, we have over 1,000 NFL D1 athletes. Now we have a new Arizona, I think, here with Zach Ertz playing, moving for the Eagles. So these are some of the highest ranked products out there in the NFL. We extended these to hockey helmets, bicycle saddles with amazing biometrics. And these are products over, 14,000 struts designed for blood flow and optimal performance. But let me just double check. Can you guys hear me?
Yes, Joe.
All right, great. So what's really happening here is that this is a transformation in how one introduces new products. Typically, people design products in CAD, but when you go from bits to atoms and you enter the real world, you're typically working with a prototyping tool that's not your manufacturing tool. You're working with prototyping materials, which is not your production materials. And you do all this because you got to cut an injection molding tool that's expensive and a big time investment before you scale it. This new world is a disintermediation of that product development cycle in manufacturing. This is way more important than the speed of the printer. This is waves of innovation that can come within hours and days that typically were spread out over months and years. And that this is really the future, that when people can design products on the means of production, really drive the innovation. I'm expecting massive new waves of innovation when you introduce these kinds of products. And just to give you some examples, despite 3D printing being around forever, you know, I'm really proud the team at Carbon got the very first new parts on new production vehicles out of Detroit. And this is, a lot of this was, you know, saving product time, design iterations, weight reduction, amazing performance. And the carbon epoxy material has got lower density than glass-filled PBT and meets all the mechanical properties. You know, we've got parts on Lamborghinis doing something similar, including, really important, this entire grill piece. And imagine if you had injection mold this, how complicated and expensive that would be for a low volume vehicle like this. But we can do this and meet the performance specs of Lamborghini. One of the most really exciting things of the epoxy system is this terrific work going on at Wisconsin, where, you know, we realize that the epoxy chemistry that we 3D print, the first step is acrylic, the second step is classic epoxy. That same epoxy resin is the same sort of coatings that are on epoxy or in carbon fiber prepreg. And so you have a really great adhesion between a 3D printed part and carbon fiber prepreg. And even these new T-joints, where the only 3D printed part is this little part in the center, which really makes some of the strongest T-joints ever shown. And this is, I think, a really great area of combined manufacturing. I'm going to skip that video, but, you know, just reinforcing again the time sequence. During COVID, we really pushed on new designs for face shields and designed them out of different materials. We also got into designing nasopharyngeal test swabs and using lattice design for making these kinds of, and we launched a medical product in 2 weeks during the height of COVID with one of our medical partners. And then we ran a 400 patient clinical trial at Stanford during the height of COVID, non-inferiority trial showing that these test swabs were terrific at DNA or the testing for the COVID virus using PCR testing. So we're really active in a lot of new areas right now, including even faster printing, multi-material printing, and recyclable resins, composites, bioabsorbable systems, lots in the software side. But let me just share with you a little bit in the area of high resolution printing. So we're building new printers with really small pixels. And what I want to show you is some at 30 microns and the opportunity here of what we've been doing with clip, and including, you know, 1.5 micron capability, you know, where you have this little guy here and the resolution that we can start getting. I think the lack of adhesion onto the window created by the dead zone is going to be extremely important as we get to these very delicate structures at this length scale. And the particular target I want to share with you, these printers for new modes of vaccine delivery. I think all of us, for the most part, are vaccinated now. That vaccine delivered via syringe into the muscle is actually targeting immune cells that are found in much higher concentrations in the dermis. We have 100 to 1,000-fold more immune cells in our dermis than we do in the muscle. And so the vaccine has typically missed them. And so there's been a lot of talk about microneedles for vaccine delivery and other things to the dermis. Traditionally, you know, microneedles were fabricated in the microelectronics fab using microelectronics fabrication techniques, typically silicon or metal-based systems, very limited design, all the same heights, expensive and limited materials. But when you think about microneedles, there's a lot of different classes of microneedles you'd love to have out of different materials. And some of them included solid microneedles, where you basically free meniscus coating process and insert the needles into the skin and let just the coating dissolve off and the needles are withdrawn, or hollow microneedles or dissolving microneedles. And so with a high resolution clip printer, we've been publishing now with different types of needles, different geometries, different heights. It's hard to make things in a fab with different diameter needles on the same area or same patch because it's hard to etch in that controlled way. Or having microneedles of different heights to avoid the bed of nails effect, or undercut structures. And so we can do these types of things, and we can do them out of a wide range of materials, including hydrogel precursors, biodegradable systems, and even water-soluble systems. This, I'm showing you some water-soluble polyacrylic acid microneedles where we vary the molecular weight of what we're printing. And so we can control the dissolution kinetics, which really allows us to control the drug delivery rates and the pharmacokinetics. And we can start changing the chemistry in different heights in the Z direction to make a payload different than the base. And so we just published this paper recently where we're using this approach with just simple rudimentary needles at this point. We've got some very exciting stuff coming. But these rudimentary needles, we've been coating with sugars in a dip coating free meniscus process on these patches that are not molded. These are precision needles that are very sharp. They're very inexpensive to fabricate. They're coated with different cargoes, and we can deliver those into the skin, and we're delivering them as in a cryoprotectant like sucrose. And not our work, but work out of the literature has shown that these can be really terrific at stabilizing protein-based subunit vaccine systems for long periods of time at room temperature. So this should have a big impact. But what's most important about this, we're targeting those immune cells in the dermis much more effectively than we are by intramuscular injection. And can you guys still hear me?
Yes.
Okay.
Yes.
All right. And by targeting the immune cells in the dermis, we see a 50-fold increase in antibody response by delivering via the microneedles that one gets from subcutaneous injections. And we get a more balanced Th1, Th2 response. So we're really excited about where this is going. We've been delivering the SARS-CoV-2 system, working with Peter Kim's lab. And again, we see a massive increase in antibody response, and now we're doing the dose-sparing studies in this regard. So let me just end, and I appreciate everyone's patience with the internet here in Silicon Valley. The promise of 3D manufacturing has been on everybody's radar for a long period of time. Mass customization, impossible geometries, local for local production, digital traceability. It's been there, but there's been a huge barrier. It's been slow. You've not really had a digital fabrication technique that can scale and be substandard materials. And I think what we're now staring at is that the unmakeable isn't. We are now making end-use parts economically at scale. And I think this future of manufacturing is now here. And there's a lot of opportunities to go beyond 3D printing that we're very excited about. And so with that, let me end and see if I'm still with you all.
Yes.
And,
Thank you, Joe. Thank you so much. Everyone has been everyone is here, and people have waited, and so we're very excited that everyone is here. We get to ask questions. If we need, we'll keep our videos. I guess without the slides, we might be okay with a couple of videos. But so if you have a question,
and again, I apologize.
That's okay. If you have a question, please post it on the chat, and I can unmute you so you can ask your questions. I'm going to kick it off with a question, Joe, about the scaling. So as you look at these applications like the microneedles, is the scaling in terms of throughput favorable, or do you have to slow down the process? And what would it look like, the economics of manufacturing this via 3D printing at scale?
Yeah, printing these small features is quick. You spend more time designing things than you do printing. Our back of the envelope estimate, and you have to think about a giga scale here, and at 100 million patches, I think 250 printers of this new type in just 3 months is the kind of thing that you could think about for 100 million at a time. So, you could easily have 1,000 printers and really hit global demands on these kinds of things.
Wonderful. We have a question here from Ali Reza Tufenchi. Let me say, See, Ali, you're able to ask your question now.
Yes, thank you, Joe. It's a great talk. I had a quick question regarding composite printing. You know, in traditional FDM, it is possible in some extent to have the different polymers printing, co-printing at the same time. I want to ask your idea about how is that possible in the clip technology? Is that any room to print multi-polymers simultaneously to leading a composite material with specific, you know, target properties?
Yeah.
Thank you.
Yeah, no, FDM and composites are almost like a pultrusion, looks very exciting. You know, I think we have some issues with the way clip is traditionally practiced regarding filler because of the gap is only about, you know, 20 to 80 microns, depending on how we run it. So we're typically using chopped fiber and other types of fillers, and we're beginning to look at anisotropy. But we have some new concepts on the road coming out where we've got new ways of introducing liquid into the gap using mechanical approaches that I think really opens up the not only high viscosity, highly filled systems, but also opens up a multi-material printing. And so these are things that we're working out the bugs now, but I'm very excited about new approaches at introducing liquids into the gap.
Thank you. We have a question from Natalie.
Yes,
Natalie.
Can you hear me?
Yes.
Perfect.
Yes.
Okay, yeah. So I was really interested in your discussion of creating products that are made from polymers or plastics and then actually being able to recycle them. I know from my research, I'm working on solar recycling, and one of the things that we're trying to make sure is that when we're developing this technology to recycle solar panels, that we're also not polluting the environment in the process, because that's counterintuitive. So I was just curious with your polymers, what research you've done to make sure that this recycling process doesn't pollute the environment in the process and be counterintuitive.
Yeah, that's a great question, Natalie. Thank you. And as a polymer person, I'm embarrassed, right? I mean, we have a polymer problem in society now. And, you know, for 30 years, doing my best in the polymer world. And I don't want the same thing to happen to additive manufacturing, you know, where we basically have a problem. And so we want to get in front of it. And I think the polyurethane chemistry I talked about is one example. We've got some other chemistries that I think are chemically degradable. But I think also what I would say is there's also business models. You could actually snap the chalk line right now in the polymer world and on technology, but you cannot rely on a miscible waste stream. You know, you've got to do better than that. And those are the things that we think about. And it's terrific that you're also thinking about it in that regard too.
Thank you. Kit, go ahead.
Yes. Thanks, Joe, for this excellent talk and accepting our invite. So my question is regarding the Adidas shoes that you showed us, how they are being manufactured, and especially the soles of these, the bottom of these, how they are being fabricated using the additive manufacturing. So can you just give us a brief idea of what kind of testing really goes in sort of manufacturing after manufacturing, so that they can be actually fitted into the final product?
After they're made.
Yes.
So, well, there's a lot of testing going in, you know, before you lock in on designs, but, you know, there is all the different sizes and all the different half sizes and all the different colors. So this is all of a sudden ballooned from a simple thought to like, this is a lot to manage. And we've introduced a new resin that's got the higher modulus that allows you to go to lighter weight. So it's been a complicated operational logistical thing, and I'm glad we've got very competent people at Carbon under Ellen Coleman's leadership and so it's hard to do all this and code on it, and we do a mechanical property testing on every one. And that stress strain curve can go right to the cloud. And so we have not only the birth certificate, but we got its first grades in school, if you will. And again, I think of every part as being alive in the cloud because of data. And what we hope to do is, you know, not this generation, but in future generations, is have a chemically recyclable resin that you can then quantify, you know, cradle to grave, and really be quantitative about data by being able to do that. So that's where we're heading with that. And there's also colorimetry. One really thing, these are easy to clean. You know, people like, what's a lattice? How do you clean it? When white foam gets dirty, it's porous, it turns yellow, and they don't look good. There's nothing worse than when white looks dirty, yellow. And these products, because of their nice surface finish, they clean beautifully, and you know, those kinds of things. So colorimetry is important, mechanical properties important, those kinds of things.
Thank you.
Yeah.
All right, we have a question from Nanzu. Should be able to unmute yourself, Nanzu. Let's go to the next question then. Petuski, should be able to unmute yourself, Bill.
Hi, very nice talk. I apologize because I had to join in about a half hour into your talk, so I missed the early part. You were talking about disintermediation, and I presume that means that the chemistries are so well understood that, and the properties that came out of it, that you could just simply design it right off and be confident about the result. What are the challenges in introducing new kinds of chemistries, and what kind of boundaries? And I'm kind of thinking in terms of, say, oxide nanoparticles, if you wanted to introduce that into your material.
Yeah, it's a great question, Bill, and you are right. The assumption is that you have a resin that's tried and true, and you got to, and more importantly, you got a supply chain that can deliver it reliably globally.
Of course.
That's hard, and I didn't appreciate it as an academic how hard that is. That's really hard. And then, you know, when winter comes for the first time, and you've got a ship with you know, 50,000 liter totes, and it's colder than anyone ever tested anything at, and things can crystallize. And I could tell you all sorts of horror stories that you're trying to establish a global supply chain that's reliable so that small changes don't matter. So those are really important. So stable resins that are shippable, scalable become really the key. And so with these iron oxide particles, it's okay to do research with, but if you want to scale, the supply chain logistics are really profound.
Mm-hmm. So it sounds like it's more on the business side is the problem from what you're saying then.
Well, yeah, we've got about 50 resins that have gone through the gauntlet.
Yeah.
Now, a lot of them are dental resins, but that's, you know, it takes a lot of work to get to things that are scalable products.
Yeah.
The research side is trivial compared to what it takes to scale.
Mm-hmm. Well, very interesting.
Thanks, Bill.
All right. All right, we're moving to Matthias Kramer. You should be able to unmute yourself, Matthias.
Yes, hi. Many thanks, Joe, for this really interesting talk. I enjoyed it very much. I was just wondering about some of the technical aspects. You mentioned that you're able to actually switch materials along the axis within single parts or within one production. And how are you going to do, how are you doing that?
Well, that's easy because all we do is we stop the print, we wash off the parts, and we put it into a different bath.
Oh, well, okay. That's way less sophisticated than I imagined from what you said in your presentation.
Yeah, but what's coming, we're very excited about, is multi-material printing in the XY direction to complement the Z direction. And we've got that coming. And we're reviewing the final figures and stuff, and we'll talk about that soon. We're very excited about that.
Thank you.
Yeah.
That indeed sounds really interesting. Let's try Nanzu again. Nanzu, you can unmute yourself.
Yeah, sorry, maybe my microphone's not working. So I have a quick question about the maybe the pricing strategy or the plan for the future systems of carbon 3Ds. So we've been very interested in the carbon 3D system, especially the M2 and L1 systems, but the pricing point was a little bit too high for the leasing. So I was wondering, like, is there going to be any like a change or any like other options for the purchase or like a lease programs for the carbon 3D systems?
So, you know, Ellen's running the details of the company now, but let me reframe the conversation a little bit in that when we came out with a new product and a new approach, and you know, what's interesting from it, this is entrepreneurship 101 kinds of dialogue here. How do you get people to join you on a journey when you're dealing with a physical product and to give them comfort that it's not going to be obsolete the next day? You know, and in the mantra here in Silicon Valley, that I've learned a lot about. It stems from, think about Tesla. Now, so our founding VP of engineering at Carbon was the founding VP of engineering at Tesla, Craig Carlson. And I've hired over 50 ex-Tesla employees into the company. The printer is not a normal printer. This printer is 100% smart hardware. Everything about it was motorized, sensored, electrified, and it's streaming to the cloud. And what that means is it's constantly being upgraded. We do software, over-the-air software upgrades to all the printers in the field every 6 to 8 weeks. And that digital twin that I showed you with all those parameters are constantly being improved. And with those improvements, we know how to print faster. We know how to print more accurately. We can introduce a new resin in a more seamless way. And it's by having a printer that's not just a bunch of collection of dumb hardware that's inexpensive. It is a connected product that you're buying basically all this content and ability to be 100% future-proofed from obsolescence. I think that's a tenet in the physical world that more products should strive to achieve. Because staring at 30 years of innovation, which I think is still in front of us, how do you get people to join you on a journey and future-proof them from obsolescence? And that's the approach that we took, having a connected product that's very sophisticated, that it's infinitely upgradable with time because of software. I hope that helps.
Thanks, Joe. We have we're still running good on time. We have 5 more minutes for questions, but it sounds like a couple more. DS Chisho.
Yes, hello. My name's Dylan Schickel. I work in the automotive industry, actually trying to industrialize 3D printing into end-use parts in the auto industry. And I had a couple questions, Mr. Desimone, about the trends that you see in the additive space. So if we go back pre-2015, before your TED Talk, which I say is a watershed moment, everybody was talking about everybody's going to have a 3D printer in their house and everybody's going to print everything they need. And of course, even at the time, keen observers knew that wasn't realistic. And so now the industry has swung towards industrial scale printers, the clip process being a real leader in that through Carbon, as well as some of the other processes. But I think now one thing that the industry is starting to see is to make one part in one platform with one process might work for simple things, but it doesn't work for everything. And sometimes there's the need to sequence processes, even different processes or processes that work at different scales. Maybe you would print a part that's the scale that you would print on an L1, but then you would need to add functionalizing at the meso scale. So you would use a tool that's something more like the 1 or 10 micron scale printers. Do you see this kind of process flow starting to come?
Oh, I think that's a brilliant observation and reflection and framework of the history and where things are going. You know, you're right. I mean, I think in the beginning, everyone thought it was going to be democratizing printing and you know, I think there's also a health and safety issue. You know, these liquid resins, just like acrylics generally are sensitizers, and even people that work in nail polish salons, you know, there's issues. So I'm not a big fan of liquid resins being in middle schools and all sorts of stuff. So that's a separate topic, but a little bit related. But now that you can scale, how do you better integrate this into a complex manufacturing ecosystem is really what you're talking about. And you know, I think that's the next wave, and that's why this is hard. This is I point at a $300 billion TAM, but you know, it's not going to be rapid because all these design wins and then all these integration issues have reliability issues that you need to walk through. And Alan Mullally and I talk about there's no such, you know, the learning curve is all about learning and learning how to do that and finding out what works and so you're right. And how do we do that? And that's where I think it's really terrific about what Arizona is investing in this is really the next phase. Now that you got reliable parts made out of reliable materials, how do you integrate that into a broader manufacturing ecosystem?
Thank you. Jose Cintas, please submit yourself.
Hey, can you hear me?
Yeah.
Yes.
Hey, that was a great talk, Joe. Yeah, I was wondering about the life cycle analysis of the parts you're printing at Carbon, especially the polyurethane ones. Have you been thinking about kind of taking those back down to the monomer, making a resin out of them again, or is this cross-linking mechanism kind of preventing that?
No, we are. We definitely are. So you know, this is at Carbon and Jason Rowland and others. But you know, polyurethanes are reversible chemistries, and you know, now my colleague Bob Weymouth and I are thinking too about, you know, all the other ways of chemically degrading systems and what is the life cycle, what is the life dependent, how long do you want the part to last? Are you designing something biodegradable inside the body and it's got to degrade a certain way? Are you do you want to do industrial composting? Or do you want to do chemical recycling? And so we're heavily focused on all of those. And the chemical recycling one, working with my colleagues, Will Tarpey and Bill, Bob Weymouth, and designing systems that can be chemically recycled after a useful lifetime. So those are, I think, the horizons that we're all want to face because we want to get to a circular economy. There's well, part of this too is leadership. You know, there's over 200 different polymers used to make a car today. That's hard to recycle, that kind of diversity. I think you can make a car out of 5 or 6 different polymers, and you can use architected design to make up the difference. In other words, one material with an intrinsic set of material properties can have a plethora of mechanical properties by using lattices, for example. And so you can now consolidate the number of materials, which will help you administer a circular economy. And so this is where policy and business comes together with technology so that you're all working together. And we're looking for leadership in the automotive industry as the 3rd largest user of polymers to take the step and lead in a totally chemically recyclable polymer industry in the automotive sector.
Okay. Thank you, Jose, for the last question. Well, this concludes the seminar today. I want to thank everyone, but especially Joe and my colleagues and co-organizers. We made it through the technical issues. It certainly will be memorable, Joe.
Yeah, I apologize again. Rain.
It will make a case for you to come back in person so you avoid those issues.
Yeah, for sure. But we need the rain in California. I just wish the internet worked.
Sounds good. Thanks, everyone. And
thank you all.
Cut some questions short.
All right. Bye-bye.